Welcome to day 1 of the STL Mastery course. Today marks the beginning of our deep dive into one of the most powerful features of modern C++, the Standard Template Library. Our session is titled Introduction to STL, What, Why, and How. We will explore what STL actually is, why it's a game changer for C++ developers, and how we can start using it today. By the end of this module, we will be writing our first STL based program and we will have our development environment fully set up for C++17 or C++20. Let's begin with the objectives of today's session. First, we will understand what STL is and why it is a fundamental part of C++ programming. Then we will explore its key components. This will include containers, iterators, algorithms, and more. Next, we will go over setting up our development environment for STL support. Whether you are using an IDE like code blocks or a lightweight editor like VS Code. Finally, we will apply what we have learned by writing a simple program using STL containers and algorithms. So what exactly is the STL? STL stands for the Standard Template Library, and as the name suggests, it's a template-based library that's part of the standard C++ library. STL provides a rich set of classes and functions that make handling data structures and algorithms easy, efficient, and consistent. Rather than reinventing the wheel every time, STL lets us use well-tested and optimized implementations of containers like vectors and maps and algorithms like sort or find. It's generic, which means it works with any data type thanks to templates. Now that we know what STL is, let's talk about why it's so useful. First of all, productivity. STL lets us write less code without sacrificing performance. Need a sorting algorithm, it's already built in. Want a dynamic array, just use vector. Second, STL is highly optimized. Most STL code is as fast or sometimes even faster than code you would write manually. It's also reusable and reliable thanks to years of testing and standardization across compilers. And finally, STL is a standard, meaning every modern C++ compiler supports it. That makes our code portable, consistent, and easy to share. STL is composed of 5 main components. First, containers like vector, map, set, PQ, and others. These are used to store data in different structures. Second is the iterators, which are like pointers that help us navigate through containers. Third is the algorithms. These include things like sort, find, count, and accumulate. They work seamlessly with containers and iterators. And fourth is function objects or functors, which allows us to create custom behavior when working with algorithms. And finally, STL includes several utility tools like pair, tuple, bitset, and newer additions like optional variant and any in C++17. Let's take a look at how STL is used in the real world. In competitive programming, STL is indispensable. Fast implementations of set, map, and heaps make solving problems efficient. In system design, STL helps with implementing caches, indexing systems, task queues, and more, all with minimal code. And in real world software development, STL is everywhere, from text editors to financial software, anywhere where structured data is being handled. Let's now set up our development environment. If you are using a C++ IDE like docs or dev C++, go into the settings and look for compiler flags or compiler options. You will want to enable support for the modern C++ standard, either C++17 or C++20, by adding the flag std equals to C++17 or std equals to C++20. This will allow you to use all modern STL features we will cover in this course. Prefer VS Code? No problem. Make sure you install the C++ and Code Runner extensions from the extensions marketplace. To compile your program, use the integrated terminal. You will run the command g++ std assign std equals to C++17 main.cpp -o main followed by dot and / main to execute it. VS Code is lightweight and fast, and with the right setup, it's perfect for STL development. Don't want to install anything? That's perfectly fine. There are several powerful online compilers you can use. Godbolt.org is fantastic if you want to see how your code, how your C++ code compiles into assembly. Great for learning. Online GDB gives us a full debugger inside the browser, and Replit is excellent for collaborative coding and running programs online. Any of these platforms will work just fine for today's hands-on. Here's a basic STL program in C++. We start by including the necessary headers, vector for our container, and algorithm for sorting. We declare a vector of integers, initialize it with some values, and then sort the vector in ascending order. Finally, we print the sorted list using a range-based for loop. This is STL at its simplest, containers and algorithms working together. Let's walk through what this code is doing. Hash include vector brings in a vector container class. Sort nums.begin nums.end sorts the vector using iterators, a key STL concept. We use a vector int to store our data and a range-based for loop to print each element. This is both readable and efficient. You will use this style often throughout the course. Now it's your turn. Write a short program where the user inputs 5 integers. Store those integers in a vector, then sort the vector and print the numbers, but in reverse order. To do this, use sort followed by the reverse function. This small exercise helps you get comfortable with STL syntax and with compiling and running C++ code in your setup. Before we wrap up, here are some quick tips. Always prefer STL containers over raw arrays. They are safer and come with useful methods. Only include the headers you actually need. This keeps compile times low and code clean. And use the while flag when compiling. It enables all compiler warnings, helping you catch bugs early in the development process. To go deeper into STL, here are some excellent resources. cppreference.com is your go-to reference for everything in the C++ standard library. hackingcpp.com offers visual guides and cheat sheets that are great for quick revision. And godbolt.org, the compiler explorer, helps you understand how your C++ code translates under the hood. It's a powerful tool for understanding, optimizing, and performance. To summarize today's session, we introduced the STL and its importance in modern C++ development. We learned about the 5 core components of STL and how they work together. We covered multiple ways to set up your development environment and wrote our first STL-based program. Tomorrow we will build on this foundation by diving into templates and iterators, 2 crucial building blocks for mastering STL. Welcome to day 2 of our 42-day STL Mastery course. Today we are going to unlock 2 of the most foundational concepts that power the entire standard template library, templates and iterators. These tools help us write generic, reusable and efficient code that does not just work for one type or situation but can be applied across a wide range of scenarios. If you have ever used a vector, map or stack in C++, you have already benefited from templates and iterators, even if you didn't realize it. So let's explore how they actually work under the hood and how you can yield them with confidence in your own code. Let's take a moment to look at today's learning objectives. First, we will gain a solid understanding of what templates are and why they matter in C++. We will compare function templates to class templates and see where each is used. Next, we will discover how STL is fundamentally built on the idea of templates. Without them, generic containers like vector int or map string int would not exist. Then we will dive into iterators, powerful tools that allow us to navigate through STL containers efficiently. Finally, we will go beyond basic syntax and examine different types of iterators: input, output, forward, bidirectional, and random access. Understanding these categories will make us a more flexible and efficient programmer. So why do we even need templates? Imagine you wanted to write a function that adds two numbers. You could write one for integers, one for floats, another for doubles, but that's not scalable. Templates solve this by enabling generic programming. They allow us to write one version of a function or class that works with any data type, and the compiler generates the type-specific code behind the scenes. This not only reduces code duplication but also improves readability and maintainability. In STL, this is crucial. When you use vector int or vector string, you are actually using the same underlying class template, just instantiated with different data types. Templates are the reason STL containers are so flexible and powerful. Let's start with function templates. Here's a simple template function called add. It accepts two parameters of type t, a placeholder for any data type. When we call this function, the compiler automatically deduces the type based on your input. If you pass integers, it becomes an int function. If you pass floats, it becomes a float function. The result: one function definition, unlimited use cases. This improves consistency, reduces bugs, and is especially useful in competitive programming or system design, where efficiency and clarity are key. Now let's talk about class templates. Class templates follow a similar idea but on a larger scale. They define a blueprint for an entire class that can work with any data type. In this example, we have defined a box class that can store any type t. We can use this class to create a box int, a box double, or even a box string. Class templates are widely used in STL containers. For instance, vector, map, and stack are all class templates. This allows them to store anything, from primitive types to user-defined objects, while maintaining type safety and performance. The entire STL is essentially a massive demonstration of the power of templates. Let's look at a few examples. Vector t stores sequence of any type. Map k, v holds key value pairs of any type combination, and pair t1 t2 bundles two values together. Thanks to templates, STL gives us a set of incredibly versatile tools that work with virtually any data structure or algorithm. We don't need to write separate versions for integers, floats, or strings. We write it once and let the compiler handle the rest. That's not just powerful, it's elegant. Now let's shift our focus to iterators. If containers are like collections of data, then iterators are the navigators that help us move through them. We can think of iterators like smart pointers. They allow us to access elements, move forward or backward, and even manipulate data, all while abstracting away the underlying structure of the container. For example, a vector and a list store data differently, but we can use them the same iterator syntax to loop through them. This uniformity is one of STL's greatest strengths. Iterators aren't one size fits all. In fact, there are 5 main types, each suited for different containers and operations. First, we have input iterators like iStream iterator, which read data one element at a time. Then output iterators like OStream outer iterator, which allow us to write data sequentially. Forward iterators can move in one direction and are used in structures like forward list. Bidirectional iterators, as the name suggests, can go both forward and backward. These are used with list, map, and set. Finally, we have random access iterators, the most powerful type. These support pointer-like operations like indexing and arithmetic. Containers like vector, deque, and array use them. Understanding these types helps us choose the right container and write more optimized code. Here are two common ways to iterate over a vector. The first is the traditional method using an iterator object. We declare an iterator, set it to the beginning of the vector, and loop until the end. The second method uses a range-based for loop with the auto keyword. This is cleaner, more modern, and often preferred when we don't need to modify the elements. Both are valid, and choosing one over the other depends on the context. If you are writing older code or working in environments without full C++11 support, you might stick with the classic method. Otherwise, embrace the newer syntax for cleaner and more readable code. Now it's time to apply what we have learned. Try writing a swap function using templates. This will help reinforce the concept of function templates. Next, create a templated class called container T that can store and return any type of value. Practice iterating through a vector and a list using both standard and reverse iterators. And here's a challenge. Reverse a vector without using STL's rbegin or std::reverse. This will test your understanding of both iterators and indexing. Let's summarize what we have covered today. Templates are the backbone of STL. They allow us to write flexible, type-safe, and reusable code. Function and class templates simplify our code base and make it easier to maintain. Iterators provide a unified way to access elements in STL containers, regardless of their internal structure. And lastly, knowing the different types of iterators helps us optimize our code and choose the right approach for every problem. Want to go a little deeper? Explore iterator triads, which are used to determine iterator category and properties at compile time. Try creating your own custom iterator class for a data structure. It's a great way to understand how STL does it behind the scenes. Also learn about iterator invalidation, which occurs when changes to a container make existing iterators invalid or unsafe to use. This is especially important in competitive coding and interviews. To reinforce today's concepts, here's your assignment. Write a function template max of 3 to find the largest of 3 values. Build a class point t with a member function to calculate distance between 2 points. This is a great way to use class templates practically. Traverse both a deque and a list using iterators forward and reverse. And finally, take on the bonus challenge. Reverse a vector without using built-in STL methods like rbegin or reverse. This assignment will not only test your understanding but also prepare you for more complex topics ahead. Welcome to day 3 of our STL course. Today we will dive into one of the most widely used and powerful containers in C++, the vector. By the end of this session, you will not only understand how vectors work under the hood, but also you will be able to write clear, efficient code using them. Vectors are dynamic, versatile, and form the backbone of many real-world applications. Let's get started. Here's what we will cover today. First, we will understand what a vector really is, how it compares to arrays, and what makes it so powerful. Then we will explore how to declare and initialize vectors in various ways. We will follow that with vector insertion techniques, element access methods, and key behavioral insights about how vectors grow. Finally, we will solidify our understanding through a coding task and some practical challenges. Let's start with basics. A std::: vector is part of the standard template library and acts like a dynamic array. Unlike static arrays, vectors can grow or shrink in size dynamically. They store elements contiguously in memory, making them cache-friendly and fast for traversal. With built-in support for resizing, inserting, and accessing elements, vectors eliminate the pain of manual memory handling. This is why they are often a go-to choice for developers in both beginner and advanced projects. Vectors can be declared in multiple ways depending on what we need. We can start with an empty vector using vector int v. We can prefill a vector with default values using vector int v5 to create a vector of size 5 filled with 0. We can also provide an initial value like vector int v5,10, which gives us a vector of 5 tens, and with initializers list we can create and initialize in one go using curly braces. This flexibility is a huge advantage when working with different types of data or starting conditions. Inserting elements into a vector is done primarily using pushback, which appends elements at the end. It's very efficient, amortized constant time. For more control, insert lets us place elements at specific positions, though it's costlier as it might shift existing elements. Behind the scenes, when the vector runs out of allocated space, it doubles its capacity, reallocating memory and copying all elements to the new space. That's why frequent mid-vector insertions can be expensive. So always choose the right insertion method based on your use case. Accessing elements in a vector is intuitive. We can use the square bracket notation like vi for fast access, but it does not perform bounds checking. If we go out of range, it can crash our program. For safer access, we use v.addI, which throws an exception if the index is out of bounds. We also have v.front and v.back to quickly get the first and last elements. For robust and production-ready code, we prefer using at unless performance is absolutely critical. This is a common area of confusion: size versus capacity. The size of a vector is how many elements it currently holds. The capacity is how much memory it has allocated, often more than the size, to allow for future insertions. When we keep adding elements and the vector exceeds its capacity, it allocates new memory using double and copies everything over. Understanding this is essential for writing efficient code. We can manage it using functions like reverse to pre-allocate space or shrink to fit to reduce memory usage. Let's walk through a simple program. We include vector to use the container and algorithm for sorting. We declare a vector with 3 elements, then use pushback to add another. Next, we sort the vector and print the elements using a range-based for loop. This snippet shows the real power of vectors: easy resizing, built-in algorithms, and clean syntax. If you are new to STL, this is your first taste of how expressive and concise C++ can be. Time for a mini challenge. Create a vector of even numbers from 2 to 20. Then insert a new value, say 999, at the second position using insert. Finally, print the entire vector using add instead of square brackets. This quick challenge will help you get comfortable with basic operations and ensure you understand the differences between access methods. Now it's your turn to build something a bit more substantial. Write a program that reads n numbers from the user into a vector. Once all values are collected, sort the vector in ascending order using sort. Then print the elements in reverse order. Bonus points if you handle edge cases like empty input or duplicate values. This task is designed to help you reinforce what you have learned so far: input, manipulation, and output using vectors. Let's take a step back and reflect. When would you choose a vector over a regular array? How do vectors compare in terms of safety and performance? What are the trade-offs when using insertions at various points? And finally, think of real-world applications. Vectors are perfect for undo history in editors, users' input tracking, and maintaining logs. Their versatility makes them invaluable. Here's your homework. Write a function to reverse a vector in place. No new vector allowed. Next, remove all even numbers from a vector using erase remove idiom. And for a bit of a stretch, try defining a vector of structs representing students with names and marks. Sort them by marks and print the top scorer. This blends vector concepts with custom data structures, just like you will do in real projects. To wrap up, vectors are a must known in STL. They are dynamic, safe, and offer powerful functionality out of the box. Today we covered declaration, insertion, and access, all of which form the foundation for more advanced operations. In the next session, we will explore how to modify and manage vector more like a pro. Till then, keep practicing and experimenting. Happy coding! Hey there, and welcome back to our STL mastery journey. Today is day 4, and we are diving into a really important and practical part of the C++ standard template library, vector modifiers and capacity. We will often find ourselves using vectors for dynamic data, and knowing how to modify them efficiently can make our code cleaner, faster, and much easier to maintain. We will also uncover how vectors handle memory allocation behind the scenes, an essential piece for writing high performance applications. Let's take a look at what we are aiming to learn today. We will start with vector modifier functions like insert, erase, and emplace back, which allow us to manipulate the contents of our vector in powerful ways. Next, we will talk about memory management, including how vectors grow, what capacity means, and how to reverse or shrink memory proactively. Finally, we will explore best practices and common pitfalls, especially around iterator invalidation. And of course, we will end with real-world code examples and hands-on activities to reinforce our understanding. C++ vectors can come equipped with a rich set of modifier functions. These aren't just bells and whistles, they are essential tools you will use daily. Functions like pushback and popback add or remove elements from the end of the vector. Dot insert lets us place element at any position, while erase helps us remove specific entries. Then there's clear for whipping the entire container and resize for adjusting the number of elements. And finally, the modern C++ starts emplace and emplace back, which create objects directly in place, avoiding unnecessary copying or moving. Each of these has specific use cases, performance implications, and behaviors that will break down today. Let's walk through a concrete example to see these modifiers in action. We start with a simple vector of integers 1, 2, 3. We use pushback 4 to add an element to the end, making it 1, 2, 3, 4. Then popback removes the last element. We are back to 1, 2, 3. Next, insert v.begin, 0 places a 0 at the beginning, while erase v.begin plus 1 removes the second element. Finally, clear whips the entire vector. Notice how intuitive this sequence is. Each line changes the vector in a clear and controlled way, but underneath there are performance and memory considerations we will soon explore. Now let's talk about a more efficient alternative to pushback, emplace back. Imagine you are using a custom type like a point start with x and y values. When you use pushback point 1, 2, a temporary object is created, then moved or copied into the vector. But with emplace back 1, 2, the object is constructed directly in the memory of the vector. No temporary object, no extra copy. This subtle difference becomes a big win in performance critical code, especially in loops or large datasets. Always prefer emplace back when dealing with user-defined types. Let's shift gears to something less visible but equally important: vector capacity. The size of a vector tells us how many elements it currently holds, but capacity tells us how much memory it has reserved. This matters because vectors grow dynamically, and when they run out of space, they allocate new memory and copy all the elements over, which is expensive. Using reverse AND lets us pre-allocate memory, avoiding those costly reallocations. Shrink to fit does the opposite. It tries to reduce unused memory after shrinking the size. Understanding and managing capacity helps us write smoother, faster programs, especially in data-heavy context. This slide shows a common behavior: exponential growth in capacity. When we push elements into a vector in a loop, it does not grow one by one. Instead, it often doubles its capacity to avoid frequent reallocations. In this example, every time we call pushback, we print the size and capacity. You will notice that the capacity jumps even if size increases linearly. This is a deliberate design choice for performance, but it also means you might allocate more memory than needed, hence the value of rewards and shrink to fit. Here's a common point of confusion: resize versus rewards. Let's clarify. Rewards 100 allocates memory for 100 elements, but does not add them. The size stays the same, 0 if it was empty. On the other hand, resize 100 actually inserts 100 default initialized elements into the array or the vector. If you are prepping a vector for incoming data, use rewards. But if you need the elements in place, maybe for initialization or fixed length buffers, go for resize. Now it's time to put your knowledge to the test. Write a function that does three things. First, insert -1 before every odd number. Then remove all even numbers from the vector. Finally, resize the vector to only 5 elements. This exercise will help reinforce your understanding of how insert, erase, and resize interact, and how every operation affects both size and capacity. Here's another challenge: test the performance of emplaceback against pushback using a custom class like person. Use the chrono library to measure time taken during insertion. This will give us first-hand experience of how emplace really shines when dealing with constructors and object creation. It's one thing to know it in theory. Now you will see the numbers yourself. Let's recap what we have learned. You can now use vector modifiers like insert, erase, and emplaceback confidently. You understand how vector capacity works and how to optimize it with reverse and resize. You know when to use emplace over push and how to manage vector growth for performance. And perhaps most importantly, you are now aware of the subtle costs and pitfalls of careless vector manipulation. To reinforce today's lesson, here are a few practical exercises. First, build a basic book catalog system that uses pushback, insert, and erase to manage books. Second, simulate an undo feature using popback. And finally, for deeper learning, simulate a dynamic array using raw pointers and compare the complexity with STL vectors. This will help you appreciate why STL exists and how much heavy lifting it does behind the scenes. And that's a wrap for our day 4. Today we moved beyond just using vectors and learned how to control them like pros, modifying their content, managing memory, and optimizing behavior. Remember, mastery of modifiers and capacity management makes our code not only more elegant but far more efficient. Feel free to ask questions, share your thoughts, or jump straight into the activities. I will see you in the next session. Hello and welcome to day 5 of our 42-day journey to the Standard Template Library or STL. So far we have explored vectors in depth. covering their declaration, capacity management, and modifiers. Today we take it a step further. We will focus on how we iterate through vectors efficiently, safely, and idiomatically in modern C++. Here's what we will aim to achieve today. First, we want to understand all the common methods used to iterate through a vector, from the traditional index-based loop to the more modern and safer range-based loop. Next, we will compare each approach, pointing out where it shines and where it might introduce bugs or inefficiencies. We will also dive into common pitfalls, those subtle mistakes that can lead to hard to find bugs such as iterator invalidation or accidental copies. Finally, we will wrap up with best practices that we can apply immediately in our own C++ projects to improve performance and readability. Before we move forward, let's take a quick refresher. Over the last few days, we have built a strong foundation in vectors. We have learned how to declare vectors, how to insert and access elements, and how to use modifiers like pushback, insert, and erase. We also touched on memory management with functions like reverse and shrink to fit. Now, as a quick exercise, can you recall 3 vector modifiers and describe what they do? Take a moment and think. This will help reinforce your understanding before we start iterating. C++ gives us a variety of ways to loop through vectors, each with its use cases. We will begin with the index-based loop, the most classic form. Then we will move to the range-based for loop, introduced in C++11, which reduces boilerplate and is less error-prone. Next, we will explore iterator-based loops, essential when working with STL algorithms or when you need direct access to memory addresses. We will also look at const iterators, which enforce read-only access, a great tool for safe coding. Finally, we will examine reverse iterators, which allow traversal from the end of a vector to the beginning. Let's start with the most fundamental method, the index-based for loop. This is where we manually access each element using vec_i, running from index 0 to vec.size -1. It's highly flexible, letting us skip, reverse, or modify elements conditionally. But it also comes with a risk. A typo in your loop condition or using an invalid index can lead to undefined behavior and crashes. Always ensure your loop limits are correct and prefer using vec.size instead of hard coding limits. Introduced in C++, the C++11, the range-based for loop simplifies syntax and improves readability. You simply write for int val :vec, and C++ will handle the iteration behind the scenes. However, this gives us a copy of each element, meaning changes inside the loop won't affect the original vector. To modify elements, use for int val :vec. This loop is ideal when you are reading or modifying all elements uniformly without worrying about indices. The iterator-based loop is another core technique. Here we use vec.begin and vec.end to define the start and end of the range. This method is especially useful when combining loops with STL algorithms like erase, find, or insert. Though more verbose than the previous methods, it offers precise control and compatibility with the full power of STL. Be cautious with syntax and dereferencing. Small mistakes can cause major issues. Sometimes we want to iterate without modifying the vector. That's where const iterators come in. They enforce read-only access to the container during iteration, preventing accidental changes. This improves code safety and helps other developers understand that the data is not being altered. Use cbegin and cend instead of begin and end for this. It's a good habit to use const iterators in functions that only read data. Now let's flip things around. Reverse iterators allow us to iterate from the end of the vector to the beginning using rbegin and rend. They are extremely handy for problems like finding the last occurrences of an element or when processing data in reverse order. Just remember R begin points to the last element and Rn points to point one before the first. Like regular iterators, reverse iterators also work well with STL algorithms. Now that we know how to iterate, let's look at what not to do. First, modifying a vector while iterating through it can invalidate iterators. If you erase an element while inside a loop, you must update the iterator. Second, accessing a vector using unchecked indices can cause out-of-bounds errors. Use @I if safety is a concern. Third, inserting or erasing during insertion changes the internal structure of the vector, often causing bugs if you are not careful. Always test iteration logic thoroughly and refer to STL documentation when in doubt. Here are a few golden rules. Prefer range-based loops when possible. They are safe, short, and expressive. Use auto ampersand and const auto ampersand to avoid unnecessary copying and to ensure clarity in intent. Avoid modifying a container mid-iteration unless you absolutely know how to do it safely. And finally, master the erase remove idiom. It's a common STL pattern to remove items from containers efficiently. Let's reinforce today's learning with some hands-on practice. Try printing a vector using all 5 iteration methods we discussed. Then reverse print only even numbers. This will test your understanding of both filtering and reverse iterators. Next, write a loop to safely remove negative numbers. Lastly, debug a deliberately broken loop to understand common iteration errors in real-world scenarios. Let's take a step back. Why is iterator safety important? It's not just about preventing crashes, it's about building robust, maintainable code. Think about which iteration style you naturally gravitate toward and why. Tomorrow we will go deeper with real vector-based coding problems, so keep these patterns in mind, they will come in handy. Your homework for today is simple but valuable. First, implement a function called remove duplicates, which efficiently clears duplicate values from a vector. Next, solve at least 3 lead code problems that require iteration through vectors. Finally, spend some time on cppreference.com, especially the section on iterator invalidation. It's a gold mine of STL wisdom. And that wraps up day 5. Great work on mastering vector iteration. You now have a complete toolkit to traverse, filter, and manipulate vectors with confidence. As always, if you have questions, drop them in the discussion or bring them to the next session. Keep practicing, and I will see you in day 6 for a full set of vector-focused coding challenges. Hello and welcome to day 6 of our 42-day STL Mastery course. Today is where we shift gears a little. We are moving from theory to full-on practice. Vectors are one of the most versatile and commonly used STL containers, and today we will not only solidify your understanding of them but also apply our knowledge in real-world scenarios, from basic manipulations to more thoughtful problem solving. This is our vector test drive today. Let's dive in. Let's begin with our objectives for today. First, we will reinforce our foundational understanding of vectors, making sure you are comfortable with how they are declared, modified, and accessed. Second, we will move into active problem solving where you will implement what you have learned in code. Third, we will highlight common mistakes and pitfalls so we know what to avoid in interviews and real world applications. And finally, the goal is to boost our confidence when using vectors so that they become second nature in our STL toolkit. Before we dive into problems, let's refresh a few critical concepts. We should already be comfortable with how to declare and initialize a vector, either with default values, specific size, or initializer list. Access methods like the subscript operator, the at method for bounds checking, and accessors like front and back are essential. You also need to know modifiers like pushback to insert at the end, popback to remove the last element, and insert, erase, and clear for more control. Don't forget the difference between size, the number of actual elements, and capacity, which refers to the amount of memory currently allocated. Understanding these will help you not only write functional code but efficient code too. We will start with some warm-up problems to activate our STL neurons. These are relatively simple tasks but incredibly useful to build fluency. Try writing a function to sum all the elements in a vector. It's straightforward but a great place to start testing loops and iterators. Next, reverse a vector using both a manual loop and STL's reverse algorithm. Compare them. Try inserting an element at a specific position. Remember that indexing matters. Implement duplicate removal in sorted vectors. Use STL tricks like init combined with erase. And finally, the max and min values in a vector, both manually and with STL functions. These tasks may be simple, but they are core building blocks for everything ahead. Are you ready to level up? Let's move to intermediate challenges. First, try rotating a vector to the left by k places. Do it manually without building rotation functions at first. Then merge two sorted vectors into one sorted, of course. Don't forget to handle edge cases like unequal sizes or empty inputs. Next, compute a running sum where each element becomes the sum of itself and all previous elements. This is a great test of accumulation and loop control. The second largest element problem is a common interview favorite. Can you find it in one pass? Finally, try creating a frequency counter, either using a vector or combined with a map. This is an intro to combining STL containers for real utility. Vectors are simple until they are not. Let's address a few common mistakes that trip up even experienced developers. First, be careful with index out of bound errors. The subscript operator does not throw exception. At does. A lot of people confuse size and capacity. Size is how many elements are actually there. Capacity is how much memory has been reserved. If you are using vectors, don't forget to clear or resize them, or you might be building on top of slate data. And a big one, iterator invalidation. If you use insert or erase, it may invalidate iterators you are using in loops. This leads to subtle and painful bugs. Be mindful of this. Avoiding them will make your STL usage clean and professional. Now it's time to switch gears and get hands-on. You will be solving a series of problems. We recommend picking at least 4 to 6 from platforms like LeetCode, HackerRank, or Gits. You can also use the code sandbox or your local IDE. Focus on writing clean code, testing with edge cases, and following the problem constraints. This is where you apply everything from the past 5 days and build real confidence. If you hit errors, don't worry. Bugs are your teachers today. For those who finish early or want a challenge, here's your stretch problem. Implement a sliding window maximum algorithm. You will be given a vector and a window size k, and your task is to find the maximum element in every sliding window of size k. Now the catch is, do this without using the DQ container or other advanced tools. Brute force it using just vectors. It may not be optimal, but it will push your logic and STL command. Try to make it efficient, and we will look at how to optimize it in upcoming sessions. Once you have worked through the lab and stretch problem, we will come together as a group to debrief. We will review the most interesting and tricky questions, discuss how people approach them and analyze different solutions. This is a great time to learn from your peers. Often, someone's shortcut or insight will help you improve your own coding process. Feel free to ask questions or share alternate solutions. This is a safe place for growth. Before we wrap up, here's your homework. Solve at least two intermediate level problems related to vectors. Pick something that challenges you. Explore the difference between using vector int and using and vector int. Understand memory layout, access patterns, and use cases. And optionally try implementing a matrix transpose using a 2D vector. It's a fantastic way to deepen your knowledge of nested vectors and grid manipulation. And that brings us to the end of day 6. You have done some solid work today, reinforcing core concepts and applying them through hands-on problem solving. You have, if you have any questions or if there were problems you struggled with, now's the time to ask. Don't hesitate to revisit today's lab later or discuss solutions with peers. Thank you for your focus and participation, and great job taking your STL skills to next level. Hello and welcome to day 7 of our standard template library course. Today marks an exciting milestone. We are diving into our first mini project. The goal is to build a student database using the std::: vector container. By doing this, we will consolidate everything we have learned so far during week 1. You will get a chance to design, implement, and debug a small functional program that mirrors a real-world use case. This project is all about applying your skills, working with structs, vectors, input-output operations, and iterators, all in one cohesive system. Let's get started. This project isn't just about coding, it's a structured review of essential STL concepts. First, we will revisit vector operations like pushback, indexing, and iteration. You will also learn how to define and use structs to represent student data. Iterators and range-based loops will come into play when displaying or modifying data. Input and output handling will be key for interactivity. We will also explore sorting using custom comparators, which introduces more advanced vector manipulation. And finally, you will practice organizing your code into modular functions, a crucial step for writing clean, maintainable code. To manage student data, we'll start by creating a simple struct. This student struct contains 3 fields: an integer for roll number, a string for the student's name, and a float for marks. Structs allow us to treat related data as a single unit. Once defined, we can create a vector of student objects to store our database. This approach makes our code more scalable and easy to understand, as each element in a vector represents one student with all their associated information. Here's what we will be building. First, we need a way to add new student entries to our database. Then we should be able to display all the students stored in a vector. Next, we will implement a search function to locate a student by their roll number. Once found, we should be able to update their data, such as name or marks. We will also create a delete option to remove a student record from the list. For an extra challenge, you can add functionality to sort students, perhaps by marks in descending order. And finally, we will give users the ability to exit the problem gracefully. To make the program user-friendly, we will build a menu interface. Think of it like a command line dashboard. Inside a while true loop, we display the menu options repeatedly until the user chooses to exit. This interface prompts the user to enter a number corresponding to their desired action: add, view, search, and so on. Then, based on their input, the program will call the relevant function. This modular menu system not only helps users navigate the program, but also keeps your code clean and well structured. Let's break down the first 2 features, adding and displaying students. For adding, prompt the user to enter roll number, name, and marks. Store this data in a student struct and then push it into the vector. Displaying students is straightforward. You loop through the vector using a range-based or traditional iterator loop, printing each student's data neatly. These two operations form the backbone of your database and are the perfect place to begin your implementation. Searching is our first use case that involves decision-making logic. You will iterate through the vector looking for a student whose roll number matches the input. The ideal way to do this is with std::find if and a lambda function. Once a student is found, we can prompt the user to input new details, maybe a new name or updated marks, and assign them to the appropriate fields. This teaches us how to manipulate existing vector elements and reinforces concepts like conditional logic and lambda usage. Deleting records follows a similar pattern to searching. Use std::find if to locate the student, then remove them using the erase function. Make sure to handle edge cases like if the student isn't found. Sorting adds a function, slightly more advanced twist. With std::sort and a custom comparator lambda, you can sort students based on marks or names. It's a powerful example of how STL and custom logic work together for real-life use cases. Here's a sample of how your program will look when executed. The menu options are clearly displayed and the user can select what they want to choose. For example, entering 1 allows them to add a new student by entering a roll number, name, and marks. A success message confirms the operation. Keeping your interface clean, informative, and friendly goes a long way in improving the user experience. Now that your program works, it's time to test it thoroughly. Try adding multiple students, then viewing the list to ensure data is stored correctly. Test what happens when you try to search or update a non-existent roll number. Delete a student and check whether they were removed successfully. Finally, sort your list and confirm the order is correct. These test cases help us identify bugs and edge cases, ensuring our code is reliable. Here are some practical tips. Use getLine for name input to handle full names with spaces. Don't shy away from using auto and range-based loops to simplify your code. Always break your code into small, single-purpose functions. It makes debugging easier. And make sure to validate all user inputs before using them, especially in the menu. This attention to detail will help you write cleaner, more resilient code. Are you feeling ambitious? Add some more stretch goals. For instance, save and load your student data from a file using file IO. You could also replace the vector with a std::map for faster lookups by roll number. Implement grading logic based on marks to assign letter grades or GPA, or introduce auto-incremented roll numbers to streamline student entry. These extra features push your C++ skills further and simulate real-world application development. By the end of today, your goal is to have a complete functioning student database using vectors. This project is a strong foundation. It demonstrates your ability to apply STL concepts to real-world coding tasks. You will leave this session having practiced struct design, vector operations, user interaction, and algorithmic thinking. Debug it, polish it, and be proud you have just built your first mini STL project from scratch.